In this video, I want to talk about one of the most, in fact, I would say the most important distribution that will come up in this course, and really in any statistical course. It's the normal distribution. And here is a view of it here. So it's one of these bell-shaped distributions. It has really nice properties, and we'll get to them in a bit. We know it's symmetric about the mean of the distribution. So the mean of the distribution splits it into two halves. Also, the median and the mode are the same as the mean for this distribution. This is what it looks like here. This is our normal distribution. And again, it's really important, and we'll see why in a few classes' time, why this is indeed such an important distribution. But the idea is, using something called the central limit theorem, we can turn any wonky distribution into a normal distribution just by taking something called the sampling distribution, which we'll talk about again in a later class. Now, the normal distribution is really a family of distributions. You get if you have a different mean and a different standard deviation, you get a different normal distribution, but they all look kind of the same. They all look like this bell-shaped curve here. And just if you're curious, there is a formula for the curve here. It's given here. It has some pi's and some e's in it with your mu's and your sigmas, but we won't ever have to use this. This is just there for you guys to see what this would look like. And in actuality, we're thinking of this as having infinitely much data underneath this curve. This is a probability density function. But we can think of it as little tiny histogram bars where its relative frequency on the y-axis there. So we're thinking about this as the top, this curve is the top of a bunch of little bars of a histogram. And so view it that way and you kind of get the right idea of what this curve is representing. So if we have an area here, let me highlight an area. Let's say this area. So this area in green, let's say the values on the x-axis were mu and let's say, I don't know, a. Then the area here represents, so this is the probability that a random variable, let's call it random variable x, is between mu and a. So that's how we're thinking of this graph for the normal distribution. And so we're going to explore what that means in the coming slides. And of course, remember that this is indeed a probability distribution. So the whole area under this curve, all of the area, this goes on to infinity, just gets really, really thin, really, really close to the x-axis on both sides. The entire area must be 1 or 100%. So that's how we're thinking of this curve. And just as a reminder, this here is a continuous distribution. So we want to use this to model things where we take measurements like height or weight or volume or time, something like that. Anytime that we have something continuous that we measure, then we can in some sense make the normal distribution pop up, which is very, very nice. Now to get a flavor of how these parameters, the mean mu and the standard deviation sigma, affect the look of a normal distribution, I'll kind of show what happens when you change both. So if we have a normal distribution, let's say it has a fixed standard deviation, so we're not changing the standard deviation, but if we increase the mean, what happens is that I didn't draw this super correctly, but we should get something with the exact same shape, except that it's moved up higher on the x-axis so that the mean is higher. So now the mean is mu 2. But I didn't draw this exactly, but the shape of these two things is the exact same. What if we do the opposite thing? What if we fix the mean and change the standard deviation? Remember, the standard deviation is a measure of spread. So here, the standard deviation of the blue curve, well, that's less spread out than the red curve, since the red curve has a higher standard deviation. It has more spread. Remember, that's what standard deviation is telling you. So when you have a normal distribution with a higher standard deviation, it's more spread out. And if it has a higher mean, it's higher up on the x-axis. So there's infinitely many standard deviations, but what's nice about them is the area between two different points on your x-axis really only cares about how far you are away from the mean in terms of the unit of standard deviation. So what we like to do, instead of thinking about a normal distribution with a mean and a standard deviation, what we usually do is we think of the normal distribution as just how many standard deviations away from the mean you are. And if you remember from previous lectures, that's our z-score. So what I wrote here, here's our mean of 10. This is our mean. And then 12 is our mean plus a standard deviation. 14 is our mean plus 2 standard deviations. 8 is our mean minus a standard deviation. And 6 is our mean minus 2 standard deviations. We can do similarly for any amount of standard deviations away from the mean. But in our standard normal distribution, our z, we usually call it a z distribution. All we care about is how many standard deviations away from the mean are. So we say the mean itself is 0 standard deviations from the mean. 12 is 1 standard deviation. 14 in this case is 2 standard deviations. 8 is -1, and 6 is -2. And this is the idea of a z-score, right? For example, 6 has a z-score of -2, since, remember, that z is x minus the mean over the standard deviation. Since we're counting how many standard deviations we are away from the mean, so figure out the distance from a point to the mean, and then figure out how many standard deviations that is. So this is going to be 6 minus 10 over 2, and if you calculate that, you get -2. So the z-score of the point 6 in this normal distribution is -2. And just like before, let's say we had this point, I don't know, this looks like what, 13.2. What's the z-score of 13.2? Well, z is 13.2 minus 10 over 2. So how many standard deviations away from the mean is 13.2? So that is 3.2 divided by 2, which is 1.6. So the z-score of this point here is 1.6. And that's how we usually think about normal distributions, is in that standard language of how many standard deviations away from the mean you are. Okay, so let's talk about finding the area of a region under curve. And what that gives us is it gives us a probability. This finds, and I'll explain this in a second. We like that it does find probability. That's very helpful to us. So if you think of this as something like a histogram for data, well, then if we were to draw an element randomly from a set of data that had a histogram that looked like this, well, we'd expect more data to come from the center of the histogram than from the edges, since the center of the histogram has more data. So that's what we're thinking of here. So let's say we're interested in the probability that if we choose something from this distribution here, that it is less than 7. I'm telling you this is the same normal distribution that we looked at on the previous slide. It has a mean of 10 and a standard deviation of 2. So we'll set it up, and then I'll tell you how we can go about solving it. So first of all, again, it's really helpful to change this into the language of z-scores. So that's z distribution, which is the number of standard deviations from the mean. So we know 10, since it's the mean, has a z-score of 0. And let's find the z-score of 7. So that's going to be 7 minus 10 over 2, which is indeed negative 1.5. So we're asking, in terms of the language of standard deviations from the mean, if we choose a random element from this distribution, what's the probability that it is less than 1.5 standard deviations from the mean? So farther away from that, more extreme. Okay, so you could think this is a very tough thing to calculate, and in some sense you're right. However, because we have this one single distribution, this standard normal distribution, in fact, we can change our language to talk about probabilities using that. We usually use the random variable z to mean we're talking about that standard normal distribution, the number of standard deviations from the mean. We call that the standard normal distribution. So we change the language there. We're now talking about the standard normal distribution. So we can look in a table, and there's lots of different tables that are out there. I'm going to post on our course website my favorite type of table, which is I find the easiest to use. However, in real life, if you're doing this in real life, a computer would just do this for you. You'd use something like Minitab or SPSS or even Excel to calculate these for you. But because we won't have access to those during an exam or a test, we'll have to learn how to use this table. But it's not particularly hard, so I'm going to explain the table on the next slide. Okay, so this is what the table looks like, and I really like this one since it's fairly easy to use for pretty much all problems. So what this table gives you, in fact, and this is important, it gives you the area to the left of every z-score. So let me kind of draw what I mean here, what it shows us. So if here is our standard normal distribution, there's our standard normal distribution. And we look up a certain z-score, and we get a value from the table. Well, that value is this area that I'm highlighting in red. It's this area. So if we were to find the area to the left of a certain z-score, in our case it was negative 1.5, which will give us the probability of picking an element here that has a z-score of negative 1.5 or less, we simply have to look it up in our table. Now, how the table works is along the columns you have the ones and the tenths digit, and along the row you have the hundredths digit. So if we're looking for negative 1.5 in our table, well, we're looking for negative 1.50. So there's negative 1.5, and there's 0, so that's negative 1.5. So we just go across in one direction and down in the other, and where they meet is our value. So there it is there. So we know the probability that z is less than negative 1.5 is 0.06681, if you want that in percent, if you like. You don't have to convert these to percent, but I will 6.681%. That if we randomly picked an element from the distribution on the previous slide, there is a 6.681% chance that it would be 7 or less. And you'll notice that I only showed the bit of the table that has negative z-scores, but there is part of the table that has positive z-scores as well. So we can use that to find something that, for example, if we had a z-score all the way up here, we could use the positive bit of that table to find all of the area under the curve from z all the way down to negative infinity. So let's do a couple more examples using this on the next slide. Okay, so let's have that standard normal distribution just as before, and we'll say a random variable is z. Okay, so we're picking an element, and we're determining the z-score of that element. So the first question asks, well, what's the probability that z is less than 0.67 if we randomly select an element from this standard normal distribution that has a mean of 0 and a standard deviation of 1, or you can also think of it as standard deviations from the mean. Well, what do we want to find? We want to find the probability that we're in. So here is 0.67 standard deviations from the mean, away from the mean in the positive direction. So we're looking for this area. So all we need to do here is go to our table. So I'm just going to sketch the table, but you should go and have a look. And if you go to the positive bit of the table, you're going to be looking for the place where you have the column label of 0.6 and the row label of 0.07. And where they meet, you will find you get a value of 0.74857. So go across the 0.6 row and down the 0.07 column, and that's the number you get. And that kind of makes sense. This looks like it could be roughly 75% of the area under the curve. So we know that this is 0.74857. And I want to point out that drawing a diagram is a fantastic thing for these questions. I suggest whenever you're looking for a probability under a normal distribution, you do indeed draw a diagram. It is extremely, extremely helpful. So let's do B here. So for B, same idea. And we're looking for, here's our mean of 0. Here is our z value of 1.13. And we're looking for, let's say, this area this time, since we're looking for the probability that if we pick a random element from this distribution, it has a z-score 1.13 or greater. So 1.13 standard deviations from the mean or more than that. Okay, so let's figure that out. Well, remember that our table only gives us values to the left of every point. But that's okay, because we know this entire distribution has an area of 1 below it, 100%. So all we need to do is we'll just subtract off what we don't want. We don't want this area in blue. So if we subtract that off from 100%, from 1, we're just left over with this green area. So we're looking to change this to 1 minus the probability that z is less than 1.13. So again, we look in our table. We're looking for the 1.1 row and the 0.03 column, and we find that we get 0.87076. And you should follow along in your table while you watch this video as well. So that's this blue area, that's how we got that. And if we subtract that from 100%, we get the leftover area in green. So this is going to be 1 minus that. 1 minus 0.87076. And if you do that subtraction, you get 0.12924. So roughly 13% of the area is above 1.13 standard deviations from the mean. Let's do the following one now. So again, let's draw a diagram and let's talk about what we know. So here will be my diagram. Let me just I will cordon that off so it looks a little more readable. So we'll draw our normal distribution. Doesn't need to be perfect looking, just a sketch to give you an idea of what you're looking for. And we're looking for the area between negative 1.71 and, let's say here, is 0.32. So we're looking for this area here. I'll color it in yellow, I guess. And maybe this is a good time to pause the video and see if you can think about how we can use that table to find that area. So pause the video now and have a think about it. See if you can figure it out. Okay, now that we're back, well, we can use that same idea of subtraction to help us out here. Well, if we take all of the area to the left of 0.32, that'll be all this stuff that'll just kind of highlight the bottom of in red here. That's all of this. And if we subtract off what we don't want, that's this bit here to the left of negative 1.71, so we'll highlight that in blue. If we subtract that off, we're left with just the area in yellow that we're looking for, this area here. So that's what we're going to do. We're going to figure out the area to the left of 0.32 and subtract off the area to the left of negative 1.71. And again, drawing the diagram really helps us here. So this is the same thing as the probability of the area to the left of 0.32, and we're going to subtract off the area to the left of negative 1.71. And we can just look in our table similarly to the previous examples. 0.32 gives us a value of 0.65, or sorry, 62552. 62552. And less than negative 1.71. Exact same idea. I'm going to go to my table. I'm just going to look up the value. And I get that this is 0.04363. And if I subtract those, I get 0.58189. So this area in yellow is roughly 58% of all of the area under this curve. So that's really useful to know. And I just want to talk about another way of solving for this one, for part B, that is. Remember that this distribution is symmetric about the mean. So another way you could do that is realize, since it's symmetric, This is the same problem as finding the area below negative 1.13. That would be the mirror image. That would be this area that I'm highlighting in yellow now. That's the mirror image of the area to the right of positive 1.13, since this distribution is symmetric about the mean. So that gives you another way of calculating that as well. And these are the three most common types of areas that you're looking for. And in fact, anything else you can kind of piece these three methods together to do. So this is a really good toolbox for finding the probability of choosing a random element from one of these distributions and having it be in a particular area.